I should start by thanking the organizers, especially Dheeraj, for making it possible to come back to IIT, not IIT, IMSC after 26 years. So I was here in 1999, that also to visit a friend, and I've never been to IMSC. So this is an opportunity. Thank you. So I'm going to talk about dark matter halo structure around real observed galaxies, and there will be a series of talks after me. So I will make things a bit, sort of build up the story, and some of these first slides can be probably be used for the others. So this is a work which was done not by me, but mainly by my former student Manush Manju, who is in New York University right now. And so over here you can see basically these are the same galaxy. This is NGC 6946, it's from the SPARC survey. It's in optical and IR. This is observed, and we know these galaxies exist. The circles around this is supposedly the dark matter halo that we don't know. Probably that it's even larger than this. And of course, what we want to understand is basically, what we understand of dark matter from observation is basically about everything over here, but looking at stuff that's inside, or wherever, I mean, looking at visible stuff. And we have to see how these things are pans out. So this is my plan of my talk. I'm very proud of this. This is the first time I've used ChatGPT to make me a figure. And it tells me that 10% will be for motivation, 50% will be the last 40 years, and then another 40% will be what has happened in the last 1 year or 2 years, basically. Okay. Yeah, big improvement. Okay. So let's start, dark matter halos. So why do dark matter halos? Dark matter halos are the building blocks of all large scale structure. Milky Way, we live inside dark matter halo. All galaxies are inside dark matter halos. In fact, one can postulate that all matter are inside some dark matter halo or other if you make the halo smaller and smaller. This is the halo model of large scale structure. And people sort of know the first thing about it, heard this many, many times, that if you look at the density of these dark matter halos, this is a self-similar formula, universally there, irrespective of the fact that there is hierarchical structure formation, things fall in or accrete, you have a universality in the dark matter density profile, which goes by the name of NFW profile. There can be some other profile also, but more or less the same profile basically agrees with all dark matter halos in simulations. Okay. Similar universality is there in velocity also. So if you look at the distribution function of velocities, it is seen from simulations that, for example, some done by Mao et al., that over there also there is a universal profile. So there is some scale factor over there. So the universal fitting formula there depends primarily on R by Rs. So this one depended on R by Rs, except over here there is an additional shape parameter. So every R by Rs, there is another parameter that gives you universality. So basically, if you know the VDF, one can find that velocity dispersion. So all these things have some universality in it. This we know. Okay. Now, it did not start with n-body simulations. We knew how halo formed in spherical collapse. That was already done in the early 70s. People's large scale structure book has it. The Preschecter formalism of the number of halos was there in the mid 70s. However, if you look at the structure of halo, one of the first very, very influential paper is that by Bertschinger in 1985, which is the secondary infall model. And there was also a paper before it by Fillmore and Goldreich. And it is one of the most successful analytical approaches to structure formation in dark matter halos. Okay. And what is interesting is that it has stood the test of time for 40 years. There have been some changes from simulations, but people, if you want to do an analytic model, will still go back to this secondary infall. Okay. And the idea over here is that there are self-similar solutions of gravitational collapse in an omega equal to 1 universe. You can do it for a smaller omega universe. The laws will be slightly different. And it's different from primary collapse because it includes accretion of material. So outside the virial radius, there is an accretion of material, and that differs. Solutions are self-similar in nature. It's very important. And it's secondary because it involves successive infall of masses. Shells after shells fall in and form the dark matter halo. And the interesting thing is that when you solve this analytical model, you find density profiles and structures. So what about the density profile? the radial density profile sort of smoothly transits from up to the virial radius and slightly changes after that. Within the virial radius, there is a constant slope of -9/4, okay, which is steeper than the classical isothermal. And outside the virial radius, where there is this accretion, it has a slightly different slope, so it becomes a little steeper, okay. And transition is basically at this virial or terminal radius. Now, if I go from the simplest way in which Wirtzinger did, which was a top hat collapse, you do with some slightly more BBK's initial functions, these numbers will change a bit, but not much, okay. So it's a straight line in density, okay. You can look at the velocities. Assumptions are very simple. Velocities are given by this, okay. And if you look at the velocities again, up to the virial radius, it is a Paul law, okay. And outside it flattens off a bit. So there are Paul laws in velocity and the Paul law in density, okay. Once we have these two, Wirtzinger also calculated another thing which is known as the pseudo phase space density. And this is very important. This is defined like this, which is rho by sigma cubed. And this is one of the most important and universal prediction of Wirtzinger's model. It's more important because it was a fundamental diagnostic of halo structure, because it sort of closely approximates the real phase space density. So this has the same properties of the real phase space density. So you can calculate it easily from a theory or from observations, okay. And the interesting thing is that this pseudo phase space density is also a Paul law with a fixed number, a very specific number, r to the power minus 1.875. And this extends over 2 or 3 orders of magnitude in radius, from the very center to the virial radius and beyond, okay. Now this is where the most important analytic model of structure formation of halos gives. 12 years after Wirtzinger's paper, the NFW, the Navarro-Frank and White results came out, okay. And that's 28 years back. And they found that this was the density profile which I mentioned in the first slide. So there is a scale radius. So remember, the Wirtzinger's model did not have a scale radius, it was just a flat line. I will show you a figure now. It has scale radius, so there's inner behavior going as r to the power minus 1, outer behavior going as r to the power minus 3. For velocities, there was an outer which was going as 1 by r, and the inner which is going as 1 by square root of r, okay. The Wirtzinger's model basically has 0 velocity anisotropy, so it's all radial in falling pattern. In real simulations, it is not radial, so there is an anisotropy parameter, and the central region is more beta equal to 0, outside there is some anisotropy, okay. But the thing to see over here is that there are new universalities, but they are different from Wirtzinger, so not a Paul law, there is a scale which is coming over here. So now if I look at it, you see this is the density profile. So this is the density profile, and this is a Wirtzinger. Wirtzinger is a straight line, whereas this has a Paul law, so minus 1, minus 3. Okay, so a scale is introduced. Similarly for dispersion velocities, Wirtzinger is a straight line, but for NFW halos, depending on the concentration, it goes and turns over. Okay. So in density and velocity, the simple Paul law relation is no more valid for dark matter simulation halos, which is what we know all the time. What happens to the pseudo phase space density? So pseudo phase space density will come from this and this, right? If I look at the pseudo phase space density from simulations, this is what they find. And this is universal. Across different simulations, thousands of halos, you have very similar to, so only dark matter of course, very similar, very tight relation. So if you look at this figure over here, see how much scattered the density is. Over here you see how tight the relation is. The pseudo phase space density is exactly a Paul law as in Wirtzinger. So what has happened, the density and the velocity structures have changed from a simple analytic model to real simulations where things are falling in, accreting, going through, shells crossing and everything. But the pseudo Paul law, this one, the phase space, is still exactly. And this is probably due to balance of, when your density increases, the velocity also increases, things like that. But this is amazing that it's common between both the things. And there has been a lot of comments about it. Now that was what I showed was for just n-body simulations. If you have hydro simulations, what happens? So in hydro simulations, it depends on the hydro simulations. Every hydro simulation gives a slightly different number. But the important thing is, again, there is a power law, which is not 1.875, but somewhere in 1.65 or 1.7, it's a power law. Okay. And hydro simulations basically, because of the baryons inside, there's adiabatic contraction. If you have feedback, then feedback also pushes things, but the power law is still there. Okay. So it does not matter. Whereas the density and the velocity are no more power laws with some scales, the pseudo phase space density is still a power law. So this is for hydro simulations, as you can see, still a power law. Okay. So what is the picture that has arose in the last 40 years? There's a universal single power law scaling relation across the entire halo is robust for CDM predictions, whether it's n-body or hydro. Remarkable universality consistent across halo samples, different simulations, different mass halos, okay, different redshifts, doesn't matter. And so this makes it a theoretician's favorite. One can argue that it is a fundamental property of CDM, structure formation. And so there are many, many papers which is trying to understand this match. There is no consensus. To the extent this has puzzled the theoreticians so much that there even has been a paper like this. Is it a fluke of physics? Okay. So is it just a fluke that there's a match, or there's something really, really deep inside it? Okay. So why care about this phase space density? The reason is that this has a fundamental connection to the theoretical properties of dark matter halo. Anything that sort of puts energy into the halo directly or indirectly will change this CDM pseudo phase space density, right? So on the other hand, it has been shown that substructure, tidal interaction, mergers, they do not change the phase space density. So if I have a self-interacting dark matter, it will add some velocity interactions. It can change the PPSD. So you can use PPSD to look at your SIDM. For warm DM, it has initial power spectra is different. So again, there will be a change in the PPSD. So you can look at the change in PPSD to look at non-SIDM, non-CDM models. Okay. 40 years later, roughly last 2 years, what do we find? So give me the results straight away. For real galaxies, there's a systematic departure from power law. So this is if we want to construct it from observations. There's a double power law behavior. The baryonic influence of the galaxy extends far beyond the baryonic galaxy, and the PPSD scale free nature is broken, so be careful if you're using it to constrain non-CDM. Okay. So how do I do it? I will go very quickly through it. So we start with spark galaxies. These have high quality H1 and H alpha rotation curves of 175 galaxies in the spark catalog. This thing took a long time to do. So this was some other projects. Okay. So these are mostly disk galaxies, so they have disk in it. Choose galaxies with high quality rotation curve going up to the flat outer part. Okay, so then it brings down to 129 galaxies. Do your standard Bayesian analysis. Okay, multi-component dark matter, visible matter models. Make sure this is not very different from what is there in simulations, like the data and mature relations. There are 2 free parameters for the visible matter. You find those. You also look at mass to light ratios. So make things make some cuts, goes to 80 galaxies, which is a good sample. Then do something which is known as reliability cuts. I'm not going to be able to talk about reliability cuts. It's a Bayesian formalism that we sort of wrote down to say what is reliable. It is beyond best phase model selection, something called reliability, and that brings to 21 galaxies in this mass range. So this is a gold sample. On this we can find. So this is the whole sample, and from there we take out 21 galaxies. Okay. If I have densities, because from these rotation curves I can get densities. If I get densities, then from densities there's a way to go to velocities with simple assumptions of sphericity of the potential. Okay. So this is called Eddington inversion. I'm not going to go through this, but one can find the velocity distribution function. Okay. So basically I find the velocity distribution function at different radii for all these galaxies. And we can fit it very well with our own fitting function, which is much better than what Mao et al. Did in 10 years back. Yeah. Okay. So we get for all of these galaxies, we get this, and we can get the sigma from there. So give an example of these two galaxies. As you see, this is the data. You do this multimodal fits to the data. We get the dark matter component. From there, we get the densities. For each dark matter component at different radii, we know the velocity distribution function. So for different radii, we know the sigma. We know the density, we know the sigma. We can find the Q. Okay, and this we can do for 21 galaxies. Okay, so what do we get for the PPSG, the pseudo phase space? This is the answer. Here is Bertshinger's line minus 1.875, which is what the simulations also agree to mainly in body simulations. And this is what we find for the galaxies, for the gold sample of galaxies. As you go to the center, it deviates from the 1.875 line. So there is a double polar thing. Okay. So there are two. So there is a slope over here and a slope over here. So if I look it carefully, so gamma 2 is the outer slope. So Bertschinger and the simulations is what they get. Simulations get it like this. Real galaxy's slope is over here. And gamma 1 is the inner slope. Remember, if it's a gamma 1 also, even if you have a hydro, it did not go beyond this. So it would be around this region, but the real galaxy is so very different. Okay. So the Q is now a double power law. Okay, and you can find out what the different things is. A transition radius, which goes from the outer power law to the inner power law, and a systematic departure from this. Important is a systematic departure. So the pseudo phase space density of real galaxies shows significant deviation. The classic single power law is a derivative to double power law, and this is due to the baryonic influence of the galaxy. Okay. Now let us quickly look at one galaxy. So let us look at this NGC 400, this green line. This part is RD. So this is the disk of the galaxy, the scale radius of the disk of the galaxy. After the scale radius of the disk of the galaxy, the baryons die down exponentially, and there is practically no baryons beyond this. Okay, so direct influence of baryons, but you see deviation also over here, and the transition region is over here. So there is influence even after all the baryons have died. Okay. Now galaxies form in dark matter halos, you always know, and now we know that galaxies affect the dark matter halos. How? I can show this from this figure, this last figure. So if you look at the inner slope and look at the surface density of baryons, you can see that the inner slope is exponentially related to the surface density of baryons. Very, very tight relation. So if I have larger concentration of baryons, it will change your inner slope. And the idea is very simple. This baryons, it not only pulls this adiabatic contraction of the density, because the dark matters are moving in a combined potential of the baryons, and it's not a self-gravitating fluid. These velocities are larger. Okay. So this is where I'm going to stop. And before I go to the next stage, this is a figure which Manush came, and just like Manush is, he came in and said, "Sir, I think it's a very important result." So I'm going to stop over here. I think it's a significant result. The single power law QR that has ruled for 40 years is no more. Shows another powerful galaxy and halo connection. This comes from simulations. And all interpretations of modification of QR at small radii due to alternative dark matter has to first account for galaxy effect. Also, all these results, are crucial for dark matter experiments. So I'll stop over here. Thank you.
Questions? Okay. Yeah.
So, for warm dark matter, why would the PPSD change? Because in warm dark matter, once the collapse starts, you will get NFW. You may not start at all if you are suppressed on small scales, but once it starts, it goes to NFW.
One of the reasons this, the value, exact number, that changes because in the Bertschinger's model, it starts with what top hat collapse.
In Bertshinger's model, sure,
Yeah.
but if you actually go to simulations, and you look at
So there are papers which shows that your power law, this is not a double power law, the power law has a different slope in the way warm dark matter follows, because it sort of puffs up and stuff like this. Anything basically which puffs up your dark matter halo will.
no, warm dark matter actually does not puff up your halo, because once the collapse starts,
Yeah.
that velocity is much higher than the thermal velocity of warm dark matter.
Okay.
If you take it, yeah. The other one small, how do you quantify the effect of, you said, so the Eddington inversion assumes sphericity, but we know that dark matter halos are triaxial.
Yeah.
So how would you quantify?
Okay, so this is a complete, so I can talk about this a little. Eddington inversion involves the sphericity of the potential. The density, of course, just the disk is not spherical, right? So you
Yeah.
have, yeah, disk. So what you have to construct in doing the Eddington inversion is basically you have to find spherical potential, sphericalize the potential. And with the sphericalized potential, you do the Eddington inversion. And that agrees well with, so there's a difference, a 10 to 20% difference, but that will not change this result that much.
Okay.
Yeah. This is something that I answer every time I do say this question. But
A very quick question, okay.
Yeah, my question is very similar to what Orko was asking. For the Eddington inversion, don't you assume there are no major mergers recently?
Yeah.
Probably the same question, but
yeah, I mean,
yeah.
these galaxies, I don't think none of them has any major mergers recently.
How do you know that?
From the morphology of the galaxies, these are very stable disks. There's no, if there's a major merger, maybe like a half.
For Milky Way, only after Gaia we know that there was, only after Gaia we know that there has been a major merger. Right? Otherwise, it was also.
So
discussed
how you
this.
call a major merger is a very, so typically in structure formation, major merger is very m/2 mass. If it's like 10 times, or when Milky Way has a mass of 10 to the 12, if a 10 to the 10 goes through,
Yeah.
it will have a blip over somewhere. It doesn't, it's not a major merger. It doesn't, so it's a pseudo hydrostatic equilibrium is there always.
Thank you very much for the nice talk.